Welcome to another video on digital electronics. In this video we will be seeing what are counters. So counters is used to count the number of clock cycles by using a group of flip-flops which are connected together such that their states change in response to the clock input. So as and when I give a clock to the flip-flop, it will change its state. Say it is 0 now, I give another clock pulse, it will turn to 1. I give another clock pulse, it will turn to 2, and so on and so forth. So flip-flop will change its state from 0 to 1 to 2 and so on. At any time, the binary equivalent of the combined state of the flip-flop gives the number of clock cycles. What does this mean? This means that, for example, I have two flip-flops and the value is 0 0. So this is connected, the output of this is connected to this flip-flop. So currently it is counting decimal value 0 because the binary value is 0 0. After one clock pulse, say the value changes of these two flip-flops to 0 1, which means the decimal value the counter is counting is 1. After next clock pulse, say it becomes 1 0. So the decimal value of this binary equivalent is 2. And the last state, the counter is counting 1 1, which means the state is 3, right? So 4 number of clocks have passed, that is why it is counting from 0 to 3. So binary equivalent of the combined state of the flip-flops gives the number of clock cycles. So combined state of the flip-flops, like I am using two flip-flops, it will count from 0 to 3. Say if we are using 3 flip-flops, then it will count from 0 0 0 to 1 1 1, which means 7 in decimal. Usually JK flip-flop is used in toggle mode, which means what? I can also use T flip-flop. JK in T is nothing but, in toggle mode is nothing but my T flip-flop, where both J is equal to K. Right, this is my T flip-flop. Now come to the types of counters. Counters are basically classified in two categories depending on the method of clocking. One is called as asynchronous, another is called as synchronous. What is asynchronous? Asynchronous means the output of one becomes clock for the other flip-flop, the output again becomes the clock for the other flip-flop. This is called as asynchronous. What does synchronous mean? Synchronous means all the flip-flops are having same clock pulse connected throughout. That is synchronous. All the flip-flops are in sync. Asynchronous, output of one becomes the clock for another. So these are two basic categories which we'll be seeing in detail while we solve the numericals. The sequence of the state is determined by the flip-flop connection type. For asynchronous, the sequence is simple. It will go from 0 to 1 to 2 to up to wherever you want it to be. You can cut it in between also. Say this will only count up to 0 to 5. This is possible. Or it will go to from 7 to 6 to 5 to 3 to up to 0. Or maybe you can count it up to 2. So for asynchronous it is simple. For synchronous you can do random states also, from 1 to 3, 3 to 2, 2 to 5 and 5 to 1, right? This is also possible, and this depends on the flip-flop connection type. Counters are classified in two categories: up counters and down counters. Up counters count from 0 to say 7, down counters count from 7 back to 0, and so on and so forth. So this is just an example. It could go from 0 to 15 also, and 15 to 0 also, and vice versa. Counters may have different bit sizes depending on the number of flip-flops used. So if I use 2 flip-flops, I will be counting only 0 to 3, right? If I am using 3 flip-flops, then I will be counting 0 to 7. If I am using 4 flip-flops, then I am counting from 0 to 15, right? Okay, now let's go to 3-bit asynchronous counter using JK flip-flop, how this works. So I have 3 flip-flops here, J0, K0, J1, K1 and J2, K2 are the inputs to these 3 flip-flops. I have connected these to 1, which means this flip-flop is currently working as a T flip-flop. If you go back and check our flip-flop sessions, you'll find this is working as nothing but a T flip-flop or a toggle flip-flop. So flip-flop 0's output Q0 is connected as a clock to flip-flop 1. Q1 is connected as a clock to flip-flop 2. And Q2 is the output that we are getting. For flip-flop 1, we are connecting an external clock. This clock pulses we are connecting. So what will happen when I connect this clock pulses? I am making a clock pulse here. So this is negative edge triggered. Negative edge triggered. Which means whenever clock pulse is having negative edge, the flip-flop will change its state. Because it is a toggle flip-flop, so it will keep on toggling since I am giving out input as 1, right? So if you remember my JK, when I had 0, 0, 0, 1, 1, 1, sorry, 1, 0 and 1, 1, right? This was Qn plus 1. So currently what we are doing? We are doing this, the last row. I am giving J as 1 and K as 1. What is my output here? Qn bar. So this is what we are doing. This is Qn, this is 0, this is 1. So it will give the toggled output. So this is the connection. Now let us see how it is counting using the waveforms. So I hope it is clear. We are using 3 flip-flops. So 2 raised to 3, it will count 8 states from 0 to 7. And this is an up counter, and hence it will count from 0 to 7. You can also make a down counter which will do the reverse of it. So for down counter, you will take the output from bar, Q1 bar, Q0 bar and Q2 bar. That's the only difference. Okay, so see, this is the clock cycle here, and this is the negative edge. I have marked in a different color to realize where the change in the output should take place. So when I apply this clock, this is the clock pulse which is applied here, the first one, right? When we apply this clock pulse, since it is a negative edge, this flip-flop with J equal to 1 and K equal to 1, that is your J0, K0 equal to 1, what does my truth table say? It says change the output from Qn to Qn bar. So my output say initially everything is 0, right? In the flip-flop everything is 0. That is our assumption. So after this negative edge, this 0 output which is appearing here will turn to 1, because I know at 1, 1 the output is Qn bar, and initially Q was 0 because initially all the flip-flops were 0. So now it will turn to 1. In the next negative edge, this 1 will turn to 0 and so on, it will continue, right? So let's see at the negative edge how the output changes. So this is my clock pulse. At the first negative edge, my Q0 initially was 0. Now it changed, or it transited from 0 to 1. It will continue up to 1 till I get this negative edge again. Again at the negative edge, this 1 will become 0. It will continue to remain 0 till I have the third negative edge. And this will keep on continuing in all the negative edges. So this is the waveform that appears at Q0 at this output. Now this output Q0 is working as a clock pulse to the next flip-flop, right? So this is going as a next flip-flop, clock pulse. This is also a negative edge trigger. So whenever Q0 transits from 1 to 0, that is negative edge, this flip-flop will change its state. So let's see how Q1 works. So this is my Q0 which is acting as a clock. So this was the external clock which we gave to Q0. Now Q0 is acting as a clock for Q1. So now we will first mark down the negative edges of Q0. Whenever there is a negative edge, now Q1 will change its state. So initially everything was 0, so Q1 remained 0. Till when? Till I got the first negative edge of Q0. At this negative edge, it will transit from 0 to 1 because it is toggled, right? 0 to 1. It will remain in 1 till the next negative edge. It became 0. Remains in 0 till the next negative edge. Goes back to 1 and so on and so forth. Now this Q1 which we just got is acting as a clock to Q2. So we'll first write down the negative edge of this, and at this negative edge my Q2 will change. So initially it was 0, it remained 0 throughout till I got the first negative edge. It changed to 1, it remained in 1 till the next negative edge went back to 0. Let's see how this counter is counting now. So see here, initially it was 0, 0, 0, which is binary 0, but the decimal value is what? Decimal value is 1. I'm sorry, 0. So again you have 0, 0 and 1. This is decimal 1. 0, 1, 0, decimal 2. 0, 1, 1, decimal 3. 1, 0, 0, decimal 4. 1, 0, 1, decimal 5. 1, 1, 0, 6 and 1, 1, 1 is decimal 7. So this is how it is counting in binary, all the 3 flip-flops from 0 to 7. I hope the concept is clear. Thank you for watching.